All right. Welcome back, everyone, to another deep dive. Today, we're tackling something that seems deceptively simple at first glance, but trust me, it's a topic with hidden depths, and it's especially crucial for you folks over at DIY Retaining Wall. We're going deep on retaining walls with a special focus on when global stability is really important.
Oh, you're absolutely right. Global stability, it's the unsung hero, the silent guardian of successful retaining wall projects. Can't emphasize that enough.
So before we get into the nitty-gritty, let's set the scene for our listeners, right? Imagine a beautiful hillside property. Stunning views, maybe you're envisioning a retaining wall holding up a driveway or a gorgeous garden terrace. Seems pretty straightforward, right? But that wall, it's working harder than you might think.
Absolutely. It's in a constant battle, resisting the relentless push of all that soil behind it, like a hidden wrestling match happening 24/7 right under our feet. And just like in a real wrestling match, sometimes things can get a little, shall we say, intense, especially when water decides to join the party.
Okay, love that analogy. Water is not just there for the show, is it? It can really turn up the heat on that soil versus wall showdown.
You said it. Water adds weight, increases pressure, and can even weaken the soil itself, making it a much more formidable opponent for our retaining wall. That's why understanding this push and shove between the soil and the wall, it's fundamental to good design. We're talking successful retaining wall design that lasts.
So it's not enough to just build a tough wall. We got to make sure it can weather the storm, especially the sneaky, persistent force of water.
That's it. And that brings us to, you guessed it, global stability. It's about taking a step back and seeing the whole picture. Not just the wall, but the soil behind it, the foundation it sits on, even the slopes above and below. It's a whole interconnected system.
Global stability, it's the big picture thinking, the holistic approach. But what if we ignore it? What if we just focus on the wall and call it a day? What kind of risks are we talking about?
Well, let's just say it's not a pretty sight. Imagine that perfectly built wall, maybe even using top-of-the-line materials. Now, picture the soil behind it starting to shift, the foundation settling unevenly, or even worse, a slope above decides to take a slide. Catastrophic, right? Even if the wall itself is strong. If we haven't considered global stability, the whole thing can come crashing down.
And for DIY retaining wall, that's the stuff of nightmares, right? I can only imagine the headaches, the costly repairs, not to mention the potential safety hazards. Not something you want to deal with.
Absolutely not. A total disaster, best avoided at all costs. And that's precisely why a thorough global stability analysis is, well, non-negotiable for a lot of retaining wall projects. Essential, really.
Okay, so let's talk about that analysis. When do we need to sound the alarm? What are the red flags screaming, hey, we need a closer look? This isn't your average backyard project.
All right, so there are a few key indicators that should make you stop and think, we might need some expert help here. Number 1, slopes. If you're dealing with significant slopes, either above or below the wall, especially if the wall is located mid-slope, that's a big red flag. Things get complex quickly in those scenarios.
So back to our hillside property. If our wall's on a steep slope or there's a steep slope looming above it, that's a sign we need to proceed with caution.
Exactly. Another major concern is, of course, the foundation itself. If the soil beneath the wall is known for being a bit, shall we say, temperamental, prone to settling, low bearing capacity, that can spell trouble for the whole system. Be extra vigilant when working with soils that are loose, poorly compacted, or the kind that likes to swell up when it rains. You know the type.
Makes perfect sense.
Yeah.
We got to make sure our retaining wall night is standing on solid ground, right? Not quicksand. What else should we be looking out for? What other conditions raise a red flag?
Yes. Let's not forget groundwater. Tricky groundwater conditions are a definite warning sign. High water tables, potential for seepage, or what we call artesian conditions. That's where groundwater is under pressure, All of these can significantly increase the forces acting on the wall and the surrounding soil.
So water isn't just adding weight here. It's like it's ganging up on our wall from below, applying pressure from all sides.
Yeah.
Sounds like a recipe for disaster.
Oh, it can be. It definitely can be. And don't even get me started on seismic zones. Building in earthquake-prone areas, you've got to factor in the potential for ground shaking. That can amplify soil pressures like you wouldn't believe, leading to instability.
So basically, if the ground itself is rocking and rolling, that wrestling match we talked about, it goes from a friendly spar to a full-blown, no-holds-barred brawl.
You got it. And even something as seemingly simple as the type of retaining wall you choose can influence whether or not you need a global stability analysis. Different walls, different personalities.
Hold on. So the design of the wall itself comes into play. Tell me more.
Absolutely. Different types of walls react differently to loads, and some are just inherently more stable than others. Take gravity walls, for instance. They're the workhorses, relying on their own weight to resist that soil pressure. Generally speaking, they're more stable than cantilever walls, which are a bit more slender and depend on a thinner stem and a wider base for support.
So if gravity walls are like those sturdy medieval fortresses built to withstand a siege, cantilever walls are maybe a little more elegant, a bit more stylish, but they might need extra attention when it comes to global stability.
That's a fantastic way to put it. And then you have the heavy hitters, the mechanically stabilized earth walls, what we call MSE walls. They use layers of geogrid reinforcement that extend back into the soil. These guys can handle serious loads and get pretty tall, but they do require a more, shall we say, in-depth analysis. We want to be absolutely sure that the whole reinforced soil mass is playing nice and staying stable.
So right off the bat, choosing the right wall for the site, that's a huge step in ensuring global stability. No one-size-fits-all approach here.
You hit the nail on the head, and that's where the expertise of DIY retaining wall comes in. You folks have the knowledge to assess the site, spot those red flags, and make informed choices about the type of wall you need, and whether it's time to call in the global stability experts.
Being proactive, thinking ahead, it's like having a superpower in this game, right? Spotting those potential problems before they turn into real-world disasters. Saves time, money, and a whole lot of stress in the long run.
Couldn't agree more. A deep understanding of global stability principles. It's like having an extra layer of insurance for your retaining wall projects. Peace of mind.
So we've covered the why of global stability analysis, the potential risks, those red flags we need to watch out for, all those factors that come into play. But what about the how? What actually happens during this analysis? Take us behind the scenes. What's going on in the minds of those global stability gurus?
Well, it's a bit like detective work, really. Gathering clues, analyzing evidence, and piecing together a complete picture of the site and its potential for stability or lack thereof.
Intriguing. So where do we start our investigation? What are the first steps in cracking this case?
First things first, we got to get to know the site, really well. That means gathering intel on the topography, the geology, but most importantly, the soil. It's all about the soil.
Soil testing. Getting down and dirty, literally.
Yeah.
Figuring out what we're dealing with.
Exactly. We need to know everything, its strength, its weight, how much water it can hold, how it behaves under pressure, all those little quirks and characteristics. It's all crucial for understanding how that soil is going to interact with our retaining wall, with those slopes, with the whole shebang.
So we're building a personality profile for the soil, figuring out its strengths, its weaknesses, its potential for troublemaking.
That's a great way to put it. We're trying to predict how it's going to act, how it's going to react when we introduce a retaining wall into the equation. It's all about understanding its behavior.
Okay, so once we've got our soil dossier, what's the next move in our detective work?
Next, we got to figure out where the weak spots are. We're talking about identifying potential failure surfaces. This is where things get really interesting, where the real detective work comes in.
So we're picturing how the slope could fail, like where the crack's going to appear, where's it going to give way.
Exactly. We're analyzing the geometry of the slope, the soil properties, the forces acting on the system. It's a complex puzzle. And lucky for us, we've got some pretty sophisticated software programs that can help us visualize all of that, all those potential failure mechanisms, like a crystal ball, but for retaining walls.
So we're playing a little what-if game, testing out different scenarios to see where those risks are hiding.
Precisely. We're trying to anticipate how the system will respond to different loads and stresses. What happens if we get a heavy downpour? What if there's some seismic activity? We got to be prepared for anything Mother Nature throws our way.
Always be prepared. That's the motto, right? Okay, so we've identified those potential failure surfaces, those weak spots in our system. Now what?
Now it's time to crunch some numbers, figure out our safety margins. We're talking about calculating safety factors. This tells us how much stronger the system is compared to the forces that are trying to take it down.
So it's like a measure of how much oomph we've got, how much stronger our system is than it needs to be, a little buffer, just in case.
It's more than just a buffer. Think of it as a safety net. We need to be sure that our system can handle the unexpected, those surprise downpours, maybe a little earth tremor, even slight variations in soil properties. We've got to account for it all.
So we're building in a little extra muscle, a little extra resilience, just in case things get a little rowdy.
Exactly. And the specific safety factor we use, well, that depends on the type of structure, the site conditions, how much risk we're willing to accept. For important structures like retaining walls, we usually aim high. We want that extra reassurance, minimize that risk of failure as much as possible. We're talking about people's property, their homes, their businesses. Safety first, always.
Makes sense. You mentioned different methods for calculating those safety factors. Can you give us a little peek behind the curtain? What are we talking about here?
Sure, two of the most common methods we use are the simplified Bishop method and the limit equilibrium method. Now, I won't bore you with the nitty-gritty, but essentially, these methods involve analyzing the forces acting on each little piece of the soil mass, like we're slicing and dicing it in our minds.
So it's like a giant 3D puzzle, and we're figuring out how each piece contributes to the overall stability of the whole structure.
A perfect analogy. We're taking into account everything, those soil properties, the geometry of the slope, where the wall sits, and all those forces that are acting on it.
Bringing all the clues together like a good detective.
Exactly. And this is where those math equations we talked about come into play. Don't worry, we've got some fancy software programs to do the heavy lifting for us.
Technology, always saving the day. But it's still important for DIY retaining wall to have, you got to be able to interpret those results, make those informed decisions.
Absolutely. Software is a tool. It can only be as good as the information you feed into it.
Garbage in, garbage out, right. So we've done our analysis, gathered all our evidence, and we've got our stability assessment. What happens next? Where do we go from here?
This is where the fun begins. Now we take all that information and use it to guide our design. The type of wall, the dimensions, the reinforcement materials, it's all informed by that global stability analysis.
So it's like a blueprint, a roadmap for building a retaining wall that's not going to let us down.
Precisely. And it's not one size fits all. Every project has its own quirks, its own challenges. We got to tailor the design to fit the specific situation.
So it's not just about plugging numbers into a formula. It's about using your judgment, your experience, to create a solution that really works.
You got it. And this is where collaboration comes in. Remember those different experts we talked about? The geotechnical engineer, the soil expert, the structural engineer who designs the wall itself, and then the site civil engineer who makes sure the wall fits in with the surrounding environment.
A whole team of experts working in sync. It's like a well-oiled machine, everyone playing their part.
Sometimes it's a little more like a jazz band, you know? Everyone gets their solo, but it's that improvisation and communication that really makes the music work.
Love that analogy. So break down those roles for us. How does this team come together to ensure global stability?
Well, the geotechnical engineer, they lay the groundwork, literally. Soil testing, site analysis, identifying those potential trouble spots, and then the structural engineer steps in and takes all that information and uses it to design a wall that can handle the pressure, the stress, the whole 9 yards.
So the geotechnical engineer tells us what we've got, and the structural engineer figures out how to make it work.
Precisely. And then the site civil engineer comes in to make sure it all fits together seamlessly. They're looking at drainage, grading, utilities, all those things that make sure the wall not only stands strong, but plays nice with its surroundings.
Making sure it's a good neighbor, so to speak.
Exactly. And for DIY retaining wall, this teamwork approach is crucial. You guys are the link, making sure everyone is on the same page, working together towards the common goal. A safe, stable, and let's not forget, beautiful retaining wall.
Teamwork makes the dream work, bringing those great minds together.
Couldn't have said it better myself.
So we've talked a lot about global stability, the big picture, the stability of the whole system. But what about the wall itself? How do we make sure it's strong enough to hold its own in that epic battle against the soil?
Good question. That's where we get into internal compound stability, or ICS for short. It's all about those building blocks, the components of the wall itself, the blocks, the geogrid, the connections, making sure they're all strong enough and working together like a well-coordinated team.
So every brick in the wall, so to speak, needs to be strong and well-connected. No weak links.
Precisely. And there are a lot of factors that influence this internal compound stability. For instance, we've got to consider the connection strength of the geogrid, how well it grips the wall facing. We don't want it slipping or pulling away under pressure.
Right. If those connections fail, the whole system could unravel, like a domino effect.
Exactly. Just as crucial is the interaction between the soil and the geogrid. They need to play nice, you know? That soil needs to hold on to those reinforcement layers, transfer those forces back into the soil mass. Teamwork is key here.
Soil and geogrid, partners in crime, fighting those lateral forces.
That's the idea. And let's not forget about compaction. Compaction. If it's poorly done, it can sabotage the whole system, even if you've got the best materials in the world.
Back to that solid ground metaphor, compaction. Important for global stability and just as important for internal compound stability.
You got it. For you folks at DIY retaining wall, proper compaction is non-negotiable. Right equipment, compact and lifts, test the density regularly, do it right, and you'll make sure that soil and reinforcement are working as one big happy family, preventing any future settling or wall movement.
Compaction, it's the glue that holds it all together.
Couldn't agree more. And speaking of crucial elements, we can't forget about drainage. Remember our wrestling match analogy? Water can be a real troublemaker if we let it. Drainage is our secret weapon to keep it in check.
Right, we got to manage that water, make sure it doesn't get any ideas about ganging up on our wall. So how do we approach drainage design for retaining walls? What's the strategy?
First and foremost, keep that water out of the reinforced zone. Think of it as a no trespassing sign for water. We can do this by installing a drainage layer behind the wall facing usually something like gravel or a geocomposite drainage material.
So like a shield, keeping those water molecules at bay.
Exactly. But we also need to give any water that does sneak in way to escape. We don't want it hanging around, causing trouble. That means drainage pipes, either along the base of the wall or vertical pipes within the reinforced zone. We call those chimney drains.
So we're giving that water an escape route, preventing it from building up pressure and causing a ruckus.
Precisely. And of course, we need to make sure those drainage pathways stay clear. Filter fabrics are our friends here, preventing those pipes from getting clogged up over time.
So it's a whole system, not just a couple of pipes thrown in as an afterthought.
Yeah.
We've got to design a drainage system that can handle whatever comes its way for the long haul.
Absolutely. And for DIY retaining wall, that kind of attention to detail, that's what sets you apart. You understand that drainage isn't optional, it's an essential part of the retaining wall package.
Thinking holistically, seeing the whole picture, from the soil to the wall to the water, it's all connected.
Couldn't put it better myself.
Okay, so we've talked about global stability, internal compound stability, drainage. We've really covered the bases, right? But there's one more piece of this retaining wall puzzle we got to talk about. The actual forces at play, the physics of it all. I know, this is where those math equations might pop up again, but bear with me. It's not as scary as it sounds.
You're talking about the actual calculations, right?
Yeah.
Figuring out the loads on the wall, how much tension those geogrid layers are experiencing, all that good stuff.
That's it. We need to understand how hard that soil is pushing, how much those geogrid layers are pulling back. It's like, what's the muscle power behind that whole wrestling match we talked about?
I like the way you think. One of the key concepts here is what we call active earth pressure. That's the force the soil is putting on the back of the wall, trying to push it over.
So how hard is that soil shoving exactly? I'm guessing it's not exactly a gentle nudge.
It can be pretty impressive, but it depends, The type of soil, how wet it is, the slope behind the wall, even things like vibrations from traffic. And as you go deeper, that pressure just keeps building.
So the bottom of the wall is feeling the squeeze. That's where those reinforcement layers come in, right? To spread out the load, keep everything in check.
Exactly. Think of those geogrid layers as a network of tiny anchors holding everything together. They transfer that force back into the soil, preventing the wall from bulging or tipping over. Teamwork.
Okay, so how do we figure out how much force each layer is dealing with? Are there like tiny pressure gauges hidden back there?
I wish it was that easy. We rely on calculations based on, soil mechanics. It gets a bit technical. We factor in the soil properties, the depth of each layer, the angle of the reinforcement. It's a lot of variables.
Sounds pretty complicated. Time for those software programs to shine again, right?
You know it. Those programs can crunch those numbers in a flash. But even so, it's helpful for someone, to understand the basics. Knowing how those forces are calculated, it helps you make better decisions in the field.
Right. It's not just about plugging in numbers. It's about knowing what those numbers mean, how they translate to the real world, how that wall is going to perform.
100%.
Yeah.
For example, understanding tensile load, that's the force pulling on the geogrid. That's critical for choosing the right product. We're talking strength, durability.
So if we have a super high tensile load, maybe because of the soil or the height of the wall, we need a geogrid that can handle it, right? Something with a higher tensile strength.
Exactly. Every geogrid has its limit, its breaking point. We want to be sure it can handle the stress. No snapping under pressure.
It's like choosing the right rope for a tug of war. You don't want to go in with a piece of string.
Perfect analogy. And it's not just about the geogrid itself. We also have to make sure it's securely connected to that wall facing.
Right, because a strong rope's no good if the knot comes undone, right?
You got it. We calculate the connection strength, looking at friction, any mechanical features that help boost that grip. We want to make sure those anchor points are rock solid.
No matter how hard that soil's pushing.
Exactly. And this is where both the geotechnical engineer and the structural engineer, they really shine. Geotech provides the data, the soil properties, those pressures, and the structural engineer uses that intel to design the wall and the reinforcement system. A real dynamic duo.
Like a perfectly choreographed dance, every step, every move working together to create this stable structure.
I like it. And it's not just about the calculations, the numbers. It's about experience, judgment. There's an art to it.
Right, you can't just be a math whiz. You need that intuition, that feel for how these systems work in the real world, out in the field.
And that's something DIY retaining wall really has going for them. That blend of technical know-how and hands-on experience, it's a winning combination.
Understanding the science, but also having that wisdom, that instinct to know when to adapt, when to adjust based on what you're seeing in the real world.
Exactly.
Well, I think we've given our listeners a solid deep dive into the world of retaining walls. Global stability, internal compound stability, drainage, those forces at play, we've covered it all.
I hope it's been insightful, not overwhelming. The key takeaway here is understanding these principles, it's about building confidence, not complexity.
It's about approaching those retaining wall projects with that deeper understanding, the forces, the challenges, the solutions that lead to success. So listener, next time you're facing a retaining wall project, remember, global stability is your guiding star. Drainage is your friend, teamwork is your superpower, and knowledge. Well, knowledge is your secret weapon. Keep learning, keep exploring, and keep those walls standing strong.
And if you ever find yourself intimidated by those math equations, just remember, they're just a way of describing the amazing forces that shape the world around us.
Until next time, happy building.